Now we need the system view files. So for this, we are going back to this download folder. So inside this system view folder that we have unzipped, so we are going to take all of this Sager folder. So copy, system view, paste. Next, what we have in here, we have config. We need this folder also. Next, we have a sample, and inside this sample folder, we have some real-time operating systems. For example, COM, MOS. In our case, we are using FreeRTOS version 10. So we need to go inside this folder, and in here we are going to find these two files, a patch and another config. So let's copy first this config file. And we are going to paste this inside our project, inside the config folder. Next, we have a patch. We are going to copy this core patch. So from the sample FreeRTOS version 10 patch inside our project. And these two files. So let's create a folder here. Now we have copied all the files required by our project to run SystemView on the target and also make some traces. So now if I'm going back to the website, we can see here under technology what kind of traces we can do. We can capture tasks, interrupts, timers, and so on. But under this technology, we can have continuous recording using the JLink debugger. We can convert our ST-Link from our STM board to JLink, but this will not be covered by this video. So we are not going to use this continuous recording. We have single shot. This is what we are going to use. So we are going to configure a RAM buffer inside our microcontroller memory and extract the data from that buffer and load it to our host application. This single shot can be started whenever we want it. So I'm going to start it from the beginning, from the init phase. And also we have a post-mortem. This will record the latest system activity. Also, it worth mentioning that you can also make some continuous recordings using the UART or TCP/IP protocol, not only the JLink. So let's continue further. So we are going back to our project. Refresh the project. So inside the patch, we can see here that we have a diff line, and it will say these are the differences for the FreeRTOS header file with a new FreeRTOS header file. So what is with ++ needs to be added to FreeRTOS.h. And yeah, let's start doing that. So we are going to copy this, press Ctrl+Shift+R, Ctrl+V. This will open our resource, and here is the matching item with this name, so double click on it. To apply the patch, we need to find this line that is not with a plus sign. So let's find this. So this is how you apply manually the patch. So this is the line. This, if we are making some comparison between these lines and this, you can see. And we need to add something here, and after that we have this eTask get state. So eTask get state, it's here. So in this RTOS version we have also a high watermark number 2. So I'm going to add those new lines here. So I'm going to copy this. We remove the plus sign, and with Shift-Tab we make the indentation to the beginning of the line. So we have finished adding this patch. So now let's continue further. So we need to find this. So I have found it, trace ready state. And after that we need to add these lines, and after that it will follow this trace queue create. So here we are, and this is then what will follow, and here we need to add something new. We need to pay attention to these ports because this is for ARM CM0, so we don't have CM0, we don't have CM3, but we have this CM4F. So now let's add the folders that contains header files to our project build settings. So include paths. So let's see. SystemView, we have some header files in the config section, FreeRTOS, Sager. Let's see also if in syscalls are, so no, in syscalls there are none. Right click, properties, and let's add workspace, config folder, FreeRTOS, and Sager. So we are going to apply. We're not going to rebuild this yet. So let's see what else is in here. So inside this assembler file, we can see there is a header file, Sager RTT. So let's go back to the C++ build settings. So here are the GCC compiler settings, but here this with .s is an assembler file and it includes a header file. So inside GCC assembler, inside include paths, we need to add the path. So workspace, Sager, apply, SystemView configuration. So here we need to add some defines. So we will see in a moment what those defines are. Internal recorder, SystemView core CM3. This is used for the Cortex M3, M4 and M7. If you have another core, you can define the other definitions. And the buffer size is how much memory we want to reserve inside our microcontroller RAM memory to save the trace. So I have reserved 5 kilobytes of RAM. So let's proceed further. We have a SystemView application name, so we can name this as we want. Device name, so we can put here the device name, the name of our microcontroller. This will be enough for us. RAM base. Now if we are going back to our manual, here we have an example of what needs to be done. So we need to enable the debug and monitor register. So we can copy the macro definitions from here. This is for the Cortex M4. So these addresses are correct. You can verify the datasheet. So we have to put this here in the C file. Next, for the configuration, we need to go back to the manual. So this is how it is. So here, in the beginning, we need to copy this before init. What this will do, it will enable the data monitor register in case it's not enabled. So this will be done in Sega SystemView conf. We need to include this FreeRTOS inside our FreeRTOS config.h at the end. So we are going to do that. So config, FreeRTOS config at the end. So at the end means here. And now we can go to main.c and we need to include the SystemView header file, Sega SystemView.h, and before task creation, so here in the user code begin area, we need to start the configuration of the SystemView. This, if you remember, it will call this enable of the register and it will do some initialization. And this one is for when you want to start the recording. So as I said, I'm going to start from the beginning. You can put this in an event based or trigger based as you want. I'm going to start it here right before the tasks are created, and let's press build. So let's see what's the problem. So Sega RTT conf. So to solve the error before, we need to also add to the assembler paths the config file. So this problem was arise from the assembler file because it was including the file that is located under Sega, which includes the RTT configuration file, header file that is located in the config folder, and this was not added to the assembler include path. So now, if we compile, we have other errors. These are good to be like this. So let's see what are these errors. So inside the FreeRTOS, if this is not defined, it will define with index to 8. Let's see further. So inside our task.c, this is expecting an argument. So this one. And inside our FreeRTOS, the Sega SystemView FreeRTOS.h is not compliant with our FreeRTOS. So what we need to do is to put here an argument. We are not going to use it, but we need to define it here. So the error says that it was passed one argument, but it takes just 0. So let's put it. So from the definition of the FreeRTOS.h, the argument is this. So going back where the error arises, so here we need to have this argument. Next, we see here this was also with an error, so we put here the argument, here and here, so also here. So notify from ISR and notify wait, they all gave the same error. So passed one argument but just takes 0. So let's save it and press build again. So now we have completely integrated the Sega view inside our project. Let's see what have we done. So we have configured the files according to the manual, and we have inside our main function, we have included the header file of the Sega view as required by the manual. So you can read all of this manual user guide, and you can see that you need to include this. So where the main function is, you need to include this. This will be your OS. So board support init, OS, This is not a Sega related stuff. This configuration is needed. So this will need the Sega SystemView configuration, and it will also enable the data monitor register. And this line of code here, you put it wherever you want to start the recording. So I have put it in the main function. So from this point onward, the buffer will be filled with tasks and interrupts. So let's build again. Let's right click, debug as. This will send the code to our board. Let's play. So now I can say that nothing will happen. So let's put a pause or suspend the application, and we have an assertion that will fail. So let's see what's in here. So priority grouping. The interrupt controller allows the bits. So we need to call this function. So let's copy these functions inside MSP init. And I'm going to build again the project. I'm going to debug as STM. So the LED is working and the button. So for now, I'm going to keep it the modification as it is. Let's continue further. So inside the expression, we need to add an expression here. And the expression that we need to add here is Sega with underscore. And RTT. So we need to stop. So we need to stop the program. We can see that now it has stopped under the idle hook. So that's okay, because the tasks are running so fast that they don't need to consume any CPU. And from here, under the AAP buffer, AAP1, we have the address of the buffer. So now we are going to show the memory view. So this is the memory view. And let's see. So we need to take this address right here. So let's add it again. And the size of the buffer is this, that was defined by us. And how much data was written is this value. So after adding the address of the memory, we need to dump the memory. So we need to press this export button. Start address, end address will be automatically updated. So we need to put the size. We need to save this as raw binary. Here we need to put the file name. So test IT01, and the extension of the file shall be sv.dat. And we are going to save this. I'm going to save it here. You can put it wherever you want. So save the file. Now we need to open the SystemView application. So we are going to continue. And you can go to file, load data. So this is the data from today. Here is the name of the project. Here is the device. These are set inside the configuration file. So we can take another look. So here, from this part of the FreeRTOS.c file, so the string is taken from there. Let's press OK. And here we can see what was happening. So this is the 200 millisecond task, 100 system tick, a lot of system ticks. So we can go to view and let's filter only tasks only. So let's see only the tasks. This is the system tick that happens every 1 millisecond, and here are the tasks when they are run. You can view this. You can view also the context below. We can see that in the idle state we have a CPU load of 99.2%. So what this means, this is not a CPU load, this is the free time when the CPU enters the sleep mode, so we have a very little CPU load. But for a CPU load simulation, I'm going to use the hold delay. So inside this 100 millisecond task, I'm going to add here a hold delay of 50 milliseconds. So I'm going to save this, build. I'm going to debug this application. I'm going to resume the execution of the code. And after some couple of seconds, I'm going to press suspend. I'm going to the Seger RT structure. Inside the AUP array, inside the vector1, we have the location. So let's go to memory. It is the same previous location. And now I want to dump 5170 bytes. So here will be like this, and this will be 02. I'm going to load the data, so 02 name. And now if we are going to look at the CPU load, we can see that 100 millisecond task has a 52% and the idle task has only 46.